Okay, we'll go ahead. Okay. Okay, good evening. I'll welcome everyone
Good
in
evening.
this webinar session. Well, today we are celebrating Ramzan Eid, so in this occasion, I'll also like to wish everyone Eid Mubarak and hope this holy day may bring happiness to all of us, our lives and our families. As we know, this is the second lecture of our webinar series, an initiative that we undertook from MTT-S Kerala chapter to continue the learning process even in these troubled times of COVID-19 pandemic. This outbreak have severely restricted our daily activities, travel, and also our lifestyle. But slowly we have to again get back to with our lives, and of course, our learning should not stop. In fact, as you can see in the screen, we believe is a continuous process, and we believe in the motto, let us not break the learning chain. Uh, in this series, actually, we'll be covering various fundamentals and advanced topics on microwave engineering, and we'll have with us experts from academics and industry. I'd like to thank all of you for joining with us today, and we'll hope to have you for our future sessions also. Today we have with us Mr. Ayan Karmakar from Semi-Conductors Laboratory, SCL Chandigarh, under Indian Space Research Organization. He will be covering the potentiality of RF MEMS for future wireless communication systems. So let us just start the session. In the beginning, I'd like to request Dr. Chinmay Shaha, MTT-S Kerala Chapter Chair, to kindly introduce the speaker.
Am I audible?
Yes, sir, you are audible. You may please introduce the speaker.
Yeah. So, firstly, I request each and every one of you to mute your audio. I repeat, please mute your audio. Probably you should turn off your fan also if you are not in an air-conditioned room. Yeah, and please request your family members or the kids, especially the elder people, to take care of the kids because we are hearing a lot of unwanted sound. Next time probably we should have a more professional platform where we can control these voices and all. Anyway, so uh, I'm Chinmay Shah from Indian Institute of Space Science and Technology, founding and current chapter chair of IEEE MTT-S Kerala chapter. As you know, we started our journey in 2019. So firstly, I congratulate my chapter officers, Mr. Orijit and Sri Anu Muhammad, for taking this initiative along with other members. And as Sri Orijit said, this is the second series during this unprecedented COVID lockdown timing. And of course, we are thankful to Sri Karmakar, who will be enlightening you very shortly. And most importantly, we had a very good response in this event also. In fact, because of that, we had to divide the events in two sessions. Today we are having session one. Session two will be conducted for a different set of audience in the weekend. So I'll just take a minute to tell about the MTT. Microwave Theory and Techniques Society of IEEE is one of the most generous society and most generous to India as well, because MTTS has a lot of special focus towards India. We at Indian soil, we get a conference which is technically and financially sponsored by Microwave Theory and Techniques Society. Last year we did it in IIT Bombay. This year it is going to be held in December in IIT Kanpur. And apart from that, MTTS is one of the very rare IEEE societies which very holistically and a lot of care for students, professionals, and all. We do organize MTTS webinars in every month. Probably those who are members, you are getting the updates through the mail, and this is happening for last several years. And as I mentioned, concerning this unprecedented situation, we have taken this initiative, which is the second in the series, and we are going to have few more by experts from academia and industry. And as the tagline of today's event says, let's not break the learning chain. Yeah, we know all of our are having a really new and challenging time, but we have learned a lot of things during this pandemic. We know how to change our lifestyle as learners, as academicians, as professionals. We should also, try to evolve ourselves, and we can have a more focused discussion for probably in at least for a year or so in a virtual mode, because attending conferences, seminars and all will not be easy. And as most of you know, even some of the world renowned conferences like IEEE IMS, Antenna Propagation Society Conference, European Conference on Antennas, all these conferences are happening over virtual mode. So we'll continue our journey towards educating, towards enlightening with our fellow members and professionals with this kind of activities. With this, I conclude my talk and welcome all of you again. So now it's my pleasant duty to introduce the speaker, Sri Ayan Karmakar. He received his BTech from Maulana Abdul Kalam Azad University of Technology in 2005. Formerly, it was known as West Bengal University of Technology. Later, he did his master's from NIT Durgapur. He joined Indian Space Research Organization as a scientist and subsequently posted to Semi-Conductor Laboratory Chandigarh in Advanced Micro and Nanosystem Division. His research interests include design and development of LSCX and carbon passive microwave integrated circuits and antennas using silicon-based MIC and RF MEMS technology. His field of expertise are expanded in fabrication technology of various MEMS-based sensors and evolving the test strategies for the same. He engaged himself in high frequency device modeling and development of passive devices for terahertz applications using silicon micromachining. He has more than 30 publications in reputed journals and conference proceedings. He has authored one technical book named Silicon RF Technology with Springer, Singapore. He received multiple prizes and awards from Department of Space, Government of India for his active involvement and technical contribution in Hindi, Rajbhasha. He has shown keen interest to build a strong communication link between academics and industry. In this context, he has delivered numerous lectures in the invited talks series in various institutes of national importance. He serves as a reviewer in reputed referred journals like IEEE Access, RFMIC, Springer, etc. He is a fellow member of IIT India and life member of Indian Science Congress Association and Bongio Bigyan Parishad. So this is a formal introduction about Ayan, but I can tell Mr. Ayan Karmakar is one of the very few in India who has the lab facilities and who has the foundry to do real-time work in the high frequency range starting from millimeter waves and terahertz. And I am also happy to let you know that he is one of my collaborators, and we have started joint activities in this particular area. So with this, I request Sri Karmakar to take over this virtual podium. Over to you, Sri Karmakar. Thank you.
Thank you, sir. Thank you for this nice introduction. First of all, I just want
Yeah.
to thank the whole IEEE MTT-S Kerala chapter, along with Professor Shah, to Sri Arijit me to share my hands-on experience. So with these things,
Sri Karmakar, I would request you to announce the protocol, which is the third slide of your presentation, and then please go ahead with your technicalities. Yes.
All of us requested to just see, these are the protocols of our webinar sessions. So please look at it at a glance. If you have any problem or any query, you can use your chat box, or later on you can mail us also. Okay. So with these things, I just want to start my presentation. The title of this presentation is the potentiality of RF MEMS for the future wireless application. And I just want to start my presentation with a very important quote from our Swamiji. You know that every new concept has to pass through 3 stages: ridicule, opposition, and finally acceptance. And it is applicable for everything, whether it is MEMS or nanotechnology, anything. If some technology is coming into first time in our society, then people will laugh at you. Then people will raise so many oppositions, and finally, if that particular technology has some potential, then people has to accept it. That is the mantra I just want to pass to these slides, and this is the very brief outlines, and I will go through all these things. This ISRO, or Indian Space Research Organization, as we know, it's a giant organization, and it has a total 19 centers across our nations. And luckily, I am posted in this northern part in this Chandigarh area. This is known as the Semi-Conductor Laboratory, or SCL. Okay, and this SCL, you can say this semiconductor laboratory, within a single umbrella, there are a lot of facilities are there. 2 parallel fabs are running. One is 6-inch, another is 8-inch. And 6-inch and 8-inch, this specification comes because from the point of view of wafer dimension, silicon wafer dimension. What is the dimension of the wafer? Say if it is the 150 millimeter or the 6-inch, then people used to call it as a 6-inch. And if it is 8-inch, then it's known as a 8-inch. Now, in this particular center, we used to do CMOS, MEMS, CCD, all these things, and from the scratch point to the final destination. Just like we start from the wafer procuring, then we design, we have a separate team of fabrications, and after fabrications and all these things, then packaging, assembly things, and finally you have to make the systems. So you can just think this is a national foundry of importance where you can get everything under a single umbrella. That is the beauty of SCL Chandigarh. And now I will go to the main subject. Before going to the RF MEMS, I think we should know little about the what is MEMS. MEMS is nothing but it's an acronym, micro electromechanical system. From the name itself, you can understand it's the amalgamation of multiple technologies. That means from the name itself, we can understand it is the micro electromechanical system. That means electrical system is there, microelectronic is there, and finally a flavor of system is there. So sometimes people used to call it as a 3 M's, like miniaturization, multiplicity, and microelectronics. And if you look at to the history, you will find that in the 1970s or 80s, this particular technology was evolved in European and then Japan also. In respect of that evolvement, if you ask me what is the age of this RF MEMS, I will say this RF MEMS is in nascent phase, because even in outside India, it has evolved only in 1990s. So it will take some time to develop. Now people are engaged themselves throughout the globe, their wholehearted efforts to develop the various circuits. Now in this particular slides, I have intentionally put a few snaps just to show you what is the device dimension, in what scale we are talking about if we realize this MEMS circuit. If you think our WBC, RBC, all these blood particles, then you can think the MEMS device is in the order of this RBC or WBCs or something like our human hair. Look at this particular slides, how the miniaturization is going on. People have think about names also. So that's why I just want to mention as a very great quote of Dr. Feynman, there is a plenty of space under the bottom. So that's what is happening. You see, what is the device dimension and how people are trying to develop their devices within a single chip, how they want to develop the whole system. So that's why the concept of SoC, system on chip, or antenna in package or lab on chip, LOC, these concepts are coming. Or you can say, if you are talking in respect of satellite communication, you can say the CubeSats, all these things are coming. Later on, we'll see what are the very basic elements of these components of this MEMS technology. You have to look at the sensor part, you have to look at the microelectronics, then actuator and structures. All these are the main business of these MEMS, and they are interlinked with each other. And finally, you need some power supply also. If somebody asks you what is the application of this MEMS or micro machining, so the answer is everywhere or every corner of human life, because there is hardly any portion of human life where MEMS has not touched its wings. You just see the series of devices I have put here. Lastly, I have put etc. etc. because it's covering from the physical sensors to the optical domain, then biological domain, then RF domain, and according to the specification, according to the usage, people have classified the domains. Suppose if it is used only in case of physical sensors domain, then it is known as a physical MEMS. If it is used for the optical domain, then it is known as a optical MEMS. And similarly, if it is applied in case of biological system, then it is known as a biomems. And in our case, I should say this is a RF MEMS or microwave MEMS. So that is the beauty of these things. We will see how the people are approaching in these things. Now, this slide intentionally I have put for our country, because you know that there is a gap between industry and academics. And if this, if somebody can make a very good bridge between these two giants, then a very good product can come out. So many institutes are doing a lot of very good researches, but individual researchers cannot do any good throughput. So that's why a very good collaboration between industry and academics is essential. That's what I just want to give a message. Now, if I look at the what are the different processes by which we can develop our MEMS things, broadly you can classify there are 4 processes, that is bulk micromachining, surface micromachining, electroplating, and wafer bonding. Subsequent slides I will describe all these things. Bulk micromachining, from the name itself you can understand, if the bulk of the material can be removed with the help of chemical or physical etching, then it is known as a bulk micromachining. As you know that the potential substrate in today's world for MEMS business is silicon and gallium arsenide. These two are the very popular. Glass is there, but these two substrates are very popular. So if you use either potassium hydroxide and or you use some DRI techniques, and with the help of these things you can make the bulk of the substrate remove, then it's known as a bulk micromachining. And I will explain how this is essential for our antenna persons, so you will be astonished to know. And surface micromachining, you can say it's a subtractive process, and I can challenge you, this is the process you cannot attain any free hanging structure with the help of CMOS devices. So that is the beauty of our MEMS. So you, in the case of MEMS, you can have a free hanging cantilever, you can have a free hanging fixed beams, or a hanging inductor, hanging capacitors or switches, all these things possible only in case of micromachining. So surface micromachining is the process which will enable us to achieve this kind of free hanging structure, which you can understand is very essential for RF person as well as for bio persons or mechanical guys, everybody. Now coming to another two important process which I have told you, wafer bonding and electroplating. These two processes are also not present in case of standard CMOS foundry. Wafer bonding is a process. Lot of noises are coming. Participants, please just mute your things. Otherwise, lots of disturbances coming. So, in case of wafer bonding, you can just think about the wafer bonding is a technique by which you can bond.
Just hold on for a second.
Okay, sir.
Hold on for a second, please. Yeah, yeah. Orijit, can you please mute everyone while newcomers have not?
Hello, can I start?
Yeah, please start. I've muted everyone.
Hello.
Yeah,
Yeah.
you please start.
So, in case of wafer bonding and and electroplating, you can just think about, suppose in case of RF person, you know the very basic concern of the cavity or the filter is the high Q, high quality factor. And that high Q is possible only when you can achieve a high volume. Because if you just recall the very basic formula of the Q, then you will find the maximum energy contained within that structure. So that is possible only with the help of wafer bonding, I can challenge you. So that is not possible with the help of your CMOS or any other technology. So suppose standard silicon wafer is of only 675 micron, but if you want to make your silicon much more thicker, say 2 times or 3 times higher than the standard, so it is possible with the help of this wafer bonding. And this wafer bonding thing, there are two types of wafer bonding. One is known as a anodic bonding, another is known as a eutectic bonding. With the help of electric field and the glass wafers, suppose if the bonding is happening, that means you see just anodic from the name itself, you can think that with the help of the field, if this bonding is happening, then it's known as a anodic bonding. And in the eutectic bonding, suppose there are two different wafers are there, silicon wafers are there, or and with these two wafers, suppose a very thin layer of gold if you want to deposit, and then if you look at this particular figure, you can understand that how this sandwich is finally going to happen, and you can have a this kind of thick substrate, and you can have some antenna or some filter kind of things you can see. And look at this particular table. This table clearly depicts what are the merits and demerits of both of the bondings, and anodic bonding and eutectic bonding both have their own merits and demerits. And electroplating is a technique which is used in case of MEMS, because suppose if you are a RF person, you know the importance of a skin depth, and sometimes we as an engineer we used to keep this particular metallization thickness as a 2 to 3 times of that skin depth. But how it is possible in case of standard CMOS foundry? Because whether you are doing MEMS, you are basically utilizing the standard tools of the CMOS. So basically, you are using the CMOS lineup, but your process is bit different. But that particular process will not give you such a thick metal. So if you want to have some thick metal, you have to go to this particular electroplating things. So that is the things. And now I will go to the very basic things of this RFIC and RF MEMS. I think this particular slide intentionally I put it just to recall for the students how the electromagnetic spectrum looks like. And if you see this whole gamut, you will see every corner has their own importance, whether it's a licensed or a unlicensed. Every corner has their own importance, and as a human being, we always in a hunt that we will use the every corner of this spectrum faithfully and very tactfully and economically also. So, starting for that RF things, the very basic things comes from the lumped and the distributed things. I think students know that. I just want to brush up these things. Lumped component, you know, you have worked in your practical labs either in BTech or in MTech levels, whether RLC you have used. And suppose if you are using this 50 hertz line frequency, then if you calculate from the C equal to F lambda, that lambda is coming around 6,000 kilometer. And now you just think about your resistor, capacitor, or inductor dimension. what is the dimension? That dimension is very, very negligible with respect to the operating wavelengths. That's why you can think hardly there is no phase difference between the input and the output signal. So it's known as a lumped components, or you can, other words, you can say the whole property of that particular component is concentrated between the two terminal points. So that is the funda of these lump components. And if you go to the distributed component, this is reverse. If that particular component or device dimension comes in the order of the operating wavelength, so then you cannot neglect that phase difference between input and output. Then you have to think about per unit length, what is the resistance, what is the capacitance, what is the inductance is coming, RLC is coming. You have to evaluate these things. So that's why this distributed components, and whenever you are entering into this RF domain or high frequency domain, you have to think about this thing, that I am now dealing with the distributed element. I cannot allow any extra connecting wires or extra unwanted things left around me. So that is the things. And if you look at this IC things, and if you ask any RF engineer, then this planar transmission line has a lot of very, very big family, but I have just shrunk that family to for only just look at this particular things. This is the planar transmissions lines, and I think we all are very much familiar with this microstrip and this CPW things, and then coming around to the is suspended microstrip thing and pin line, then suspended strip line and non-radiative guides also. But among that, this microstrip and CPW things, these two things, I think these are the very, very popular. Most of us who are working in the PCB technologies or who are working in the MEMS, they are very much popular, familiar with these two popular planar transmission lines, because they have their own advantages. They can, their design is very easy, as well as their fabrication or the realization and technique are very simple also. So, and finally you have to think about how can I build the system, how can I test it, all these things also you have to think. Now, as I have told earlier, that the importance of the bulk micromachining can be understood with the help of this diagram. Now suppose this particular, above this black patch is nothing but our radiating element or the main antenna element, and this is your silicon substrate, and in the bottom I have put one ground plane. So now, just for a assumption, you just think that this has not been bulk micromachined. So this particular antenna is fabricated upon a thick silicon substrate. So what this particular antenna is looking around, this is looking, I have a very, very lossy substrate beneath me. So that's why I will invite my unwanted waves like surface waves, like leaky waves, and all these waves particularly gives rise to the heat dissipation. So I can say there is a source of loss. So because in the microwave there are basically three fundamental losses are there. One is ohmic loss, another is dielectric or substrate loss, and third one is the radiation loss. If you think about the antenna particular things, then you just forget about this radiation loss, because their radiation is wanted things. We will look upon that particular thing. So we will just focus about these two losses. Now this conductor loss, it cannot be minimized. It can be minimized up to some limit, but it cannot make a zero. But whether you are looking around this particular substrate or the dielectric loss, you just think this is a very big column of error has been made. So finally the whole equivalent capacitance or the whole equivalent effective permittivity has gone decreased. So you can now think the very thin membrane or very thin layer of silicon is there, and that silicon, very thin layer of this particular silicon is not at all mattering a lot. So that's why basically this substrate loss is going to be diminished, and as a whole you are getting these advantages: less loss, that means I have already told surface wave is eliminated, and as a whole you are getting the whole bandwidth, higher bandwidth you can get, and sensitivity to change in the epsilon r also, less dispersion effect also you can. So that is the importance of this bulk micromachining in case of this you can say this the very important thing for antenna engineers. And if you look at this potential of the RF MEMS, you can just think about why this particular technology is going to happen to be so much popular in nowadays. It will offer you a very small size, shape and volume. Linearity business is a very good thing, and I think if you talk about any Schottky diode, FET, HEMT, all these things, they are all suffering for this second point. So that is the things. And if you think about this insertion loss point of view, RF MEMS technology is the technology which will offer you less than zero point 0.5, even sometimes it comes as a 0.1 dB insertion loss. So now think about how much less loss is offering. So how much less effort you have to give at the amplifier chain. So how much cost you are basically minimizing, and how efficiently you are designing your system in a very economical manner. So that is the beauty of these things. And finally, it negligibly, or it has a zero power consumption. So that is the beauty of this thing. And look at the application. In the next slide, I will show you how it is replacing, how it has the potential to replace the important building blocks. I will show you. And this particular slide is showing you the how the exponential growth of this particular RF MEMS things is happening. You see, this is an exponential growth, and the source is also, I have cited the source also. And coming to our semiconductor laboratory, we have started that things, the very small group in the 2006. Earlier, we have a CMOS foundry. It's very popular for this CMOS foundry. And parallelly, we started these things, the MEMS things also. Initially, we have characterized that things, how this silicon can be used, whether normal silicon wafer or high resistive silicon wafer, and how the loss can be minimized, how the oxide nitride stack can be modeled, all these things, and finally how a compatible process can be developed. And with all these simulation tools, we started our things. Now look at this particular slide which I was talking about. So you just look at things, these highlighted portions, this greenish color highlighted portions, these portions can be replaced faithfully with the help of RF MEMS. It has the potential to replace all these things. Now think about how the scenario will got changed. Your whole system, your whole transceiver component will come in a single chip, and how the easy it will be for any engineer. Now what are the different techniques worldwide? If you see, one technique is very popular, that is known as a bottom to top approach. So first of all, you will target the very basic components like switches, then inductors, capacitors, all these things. If you are succeeded in all those things, then you have to think about the next level of higher level, little bit complicated. Just like the immediate application of switch is the phase shifter, then filter, all these things. And if you are once again through all this particular channel, then you have to come to the finally system level, that is the phased array antenna things. So that is the final things, or say Butler matrix or beamforming networks, all these things you will think about all this. So that is known as a bottom to top approach, bottom to top approach. And worldwide, even in our semiconductor laboratory also, we used to approaching this very popular approach. And I think this particular slide is a self-explanatory. Whether you have a design First of all, you have to some concept, then you have to design, integrate, and finally you have to go to the production. This is a very natural law of any design engineers. And if you look at the specifically for the RF design, you have to think about this particular thing. You have to think how this particular hexagon has to be completed. Now, whether you are working in a RF domain, then you have to think about, you have to tackle the noise, and this particular noise may be of device, maybe of your passive components, maybe of some power supply. So there may be multiple sources of noise. You have to tackle, you have to trade off all these things. So that's why I put. Then you have to think about how can I tackle my linearity problem. If we were thinking about say some LNA business, then you have to think the K and the gain, this how these things can be tackled, and a very good trade-off has to be made. And then frequency response and gain finally. So these are the very important things, and this is a very common for any RF. So similarly, this is applicable for RF MEMS also. And with these things, I just want to enter into this little bit on the antenna field, and I just want to show how this particular RF MEMS can be just acts as a blessings to antenna engineers. You can see, you know that this planar antenna business, this has started from the 1947 to 50, but that particular concept was conceived in the 1947 and 48, but the actual development was few years later because of the lack of some technologies. And if you look at the whole history, if you look at the whole literature survey, and you know that this particular planar antenna has a lot of advantages. It's a lightweight, it is used in ground, it is used in airborne devices, it's miniaturized in size, it can be fabricated very, very easily. Batch processing can be applicable. If you go to the medical field, it's applicable there also. But it has some issues also. You know those issues. It has a very, very low gain. Its radiation efficiency is also low. It's suffering from surface wave loss, leaky wave problems also, low directivity, and that's why now MEMS technology has come just as a blessing to alleviate all those issues. We will look upon how these issues can be alleviated. Now, I have already explained how the bulk micromachining can be used to eliminate the surface wave loss. Now I will explain the same thing with the help of transmission lines, that very basic things. You know that RLGC, these four parameters are very, very common, and these four parameters basically explain the whole transmission line theory. And if you go to the very basics of these transmission lines, you will see this G and C, these parameters are essential to express the substrate or the dielectric loss, how the leaky capacitor is behaving, how the leaky capacitor is showing that how much leaky it is, how much wave is trapped within the substrate. So that can be explained with the help of this G and C. And with the help of this removing with the aid of bulk micromachining, you can think now what will be the effective permittivity of this substrate. That means a high column of air and a very thin layer of silicon will yield basically a effective permittivity very, very near to air. So if it is very, very near to air, so all the problems has gone. Now, if you look at to the modern day antenna engineering, you will be astonished to know now people are thinking about 3D integration or the vertical integration. So vertical or 3D integration is a technique which will basically minimize the footprint of the antenna, but it will enhance the efficiency of the antenna in a very smart way. How? So there are multiple layers can be integrated, and I have shown here intentionally an exploded view. Suppose one micro-machine patch antenna array is there, and in another layer you are basically integrating antenna feed network. So with the help of micro-machining, suppose if you are developing different flavors of antenna, and finally with the help of wafer bonding, if you can integrate those wafers, so at the end of the day you will get a beautiful antenna which will give you a very good efficiency and a very small footprint but a very good antenna. You see, people have reported up to 94 gigahertz also, this kind of process they have developed, and Professor Gabriel Revis basically developed these things. And if you think about the different feeding techniques, you know that aperture coupling is one of the important feeding techniques which is used in case of this patch antenna. And this particular aperture coupling is a feeding technique which is used for this patch antenna to broaden the impedance bandwidth of the antenna, as well as its directivity will be excellent one with that broader bandwidth. So that is also possible with the help of MEMS. Now look at this particular figure. This particular figure is showing basically two different wafers. I have intentionally put these figures just to differentiate these two different colors with the two different wafers. This ash color is of a silicon wafers and which has a matching stub, and another wafer is there which has been bulk micromachined, and this particular bulk micromachined wafer has a silicon antenna, and this particular antenna has been fabricated on high resistive silicon with this kind of bulk micromachine. So that much of thick air column is there, and now you think about how this coupling thing is going on. Now this is the ground slot for this antenna, this is the ground plane, and with that ground plane this kind of slot is there. This is the slot from where this particular electric field can penetrate faithfully and intentionally, and it can interact with the stub to have a excellent performance. So this is the beauty of this RF MEMS, where you can achieve a lots of antenna problems. Now look at this antenna array. You know the single antenna cannot serve your purpose. You need antenna array, and in practical business you need a lot of antenna array, huge antenna array. And whenever you have some array, you have some coupling issue, and you know those coupling issues, sometimes this coupling issue can be a very detrimental effect, because this coupling can be of two types. It may have some positive, it may have some cross interference. So if you want to remove those cross interference things, then your polarization impurity and all these losses will be obviously it will be improved. So that is also possible with the help of micromachining. With the proper micromachining things, you can think, yeah, how this coupling is improved from this dB to that dB. So that is the things, and people have shown these particular things up to 110 gigahertz. And look at this high quality microwave filters. Initially, at the beginning, I have told you a filter, it has a figure of merit of Q factor or quality factor, and this particular Q factor can be improved with the help of if that filter volume can be enhanced. Now just think about your own room where you are just sitting during this webinar session. Now just think about if that height of that room, if it is increasing, then automatically the volume will be increased, but xy dimension I am keeping the constant. So this volume can be increased with the increasement of this height. Now this, so now suppose this particular room is of only 675 micron thickness, that is the standard thickness of your silicon. So you are not able to achieve the desired Q factor. So what you will do, your analytical theory or your analytical calculation is suggesting you just enhance your H. So you can enhance your H by double, or say by making the 3 times or 4 times higher than that of the standard one. That means you are basically multiplying n into 675. So that is possible with the help of this MEMS things, with the help of wafer bonding, specifically if you ask me. And with these things, whether this particular silicon has a lot of potential or not. So that's why I put these things. And recently, as Dr. Shaha told already, that last year we had some book also. That book is fully dedicated on SiRF technology, that is silicon RF technology. Why this particular silicon? Why people are thinking about system on chip? So that's why one proverb is there: yesterday's chip is now today's functional block. Now you just think about your BTech or school level study. You have studied that 8085 microprocessor. Now people are thinking about microcontroller. Now the future generation are very much accustomed with these mobiles, the laptops, notepad, all these things. These are the nothing but the blessings of SoC. So you have to penetrate into this silicon RF technology, and this is the paradigm shift. Now you can think the how the system on board concept is now converging to the system on chip concept. And if you go to the very basics of these transmission lines, you can see this how this RLGC 4 parameters are basically dominating. And if you think that this particular substrate loss, this is nothing but a function of two things. One is resistivity of that particular substrate, or in other words, the conductivity of the substrate, and the frequency of the operations. Now, if you look at the silicon, it has basically two modes of operation. One is known as a slow wave modes, another is quasi-TM modes. And normal silicon wafers, or the silicon wafers normally used for the standard CMOS foundry, that has the resistivity of around 0.01 centimeter to 10 ohm centimeter maximum. But this is not sufficient for a RF engineer. For a RF engineer, they need some high resistive silicon, which is made of FZ or float zone process, which has these three particular characteristics. It has the uniform resistivity throughout the thickness of wafer. It has the acceptable radial as well as the axial resistivity gradients, and the stable resistivity throughout the device processing. Apart from these things, intentionally I have put this very simple formula to explain these things. One parameter that is known as a dielectric relaxation frequency, that is denoted here as a FC. This particular parameter basically dictate, suppose if you are taking a substrate, and in the parallel of this substrate, you are basically applying some electric field. And this electric field is a alternating nature. And this electric field, as it is alternating in nature, so sometime it is applying and sometime it is going to be zero or reverse after some point. So whether you have some dielectric, but that dielectric in practice cannot be a pure dielectric. It has some trap charges, it has some trap ions. So these ions, these charges, it will be polarized with the application of that applied electric field. And suppose if you were removing immediately that electric field, so basically what should be done? What should happen? So those polarization nature, it should be minimized or it should be neutralized. But in practice, it's not happen. It takes some times. It takes some period. So that is dielectric relaxation period. So from there only this FC is coming, and which is dominated by this R and C, this R and C of the substrate material. So that is related with the resistivity and the permittivity of the substrate. So that things you have to calculate whenever you are dealing with the silicon or gallium arsenide before entering into the RF MEMS things. And popularly, normally in our foundry, we used to go by these standards techniques. Suppose if we are dealing with these RF MEMS things, either we go for a thick oxide layer deposition or a thick nitride or a thick polyimide, or we can have some oxide nitride stack or simple nitride stack or oxide poly stack. These are the standards protocols, and it has some proper characterization process, proper characterization data by which we have concluded up to this. And you know, one of the very important thing is that in the application of the antenna is the phased array antenna. This phased array antenna is not a new thing. This name you may not heard previously, but I will give example. Suppose if I am now talking with you people, and some of the participant is really very much reluctant to hear my voice, so he will look at me, but he will not hear my voice from the core of his heart. But somebody is very much interested. She is really looking to my PPT, and trying to understand something, and he will pop up something there. Please explain all these things later on. So that is the business of this phased array smart antenna concept. Suppose I just want to hear you, then I will hear your voice only. My mind is basically acting as a smart antenna. So that concept of the mother nature is implemented in the antenna engineering field. So that is the smart antenna. Few portions or in the few directions, if you want to propagate or if you want to communicate, then you just activate your things. So that is the you just think in the legacy earlier it was a mechanical scanning process. Now people have to see the electronic it doesn't suffer from the wear and tear problem that of mechanical problem. And Jimbalon geared all these particular negativity or all these bulky things has been removed. Electronic thing you can just think about how much tiny, how much small things are there, and people have also classified into these things as a active and passives. And active and passive, you can just think about how the active and passive antennas are there. So accordingly, these things are happening, and you just look at this particular things here. 180-degree scanning, it is showing how this scanning can be done. It can have some 360-degree, and as an example I have just put these things. And now the how the scanning is done, you just think about these things. So suppose if you have a lot of antennas are there or a lot of arrays are there. Now you, if you want to control, if you want to have want to send some signals which will basically control the which portion of the antenna will be activated, or which portion I just want to activate, or which portion I want to deactivate. Accordingly, so transmitter will send the signals, and basically it's a phased array networks, and phased array networks consist of a phase shifters, and that phase shifter things is the main important things which comes out as a RF MEMS switch. Look at this particular slide carefully. This particular slides has been taken from a very popular book, RF MEMS Theory, Design and Technology by Professor G.M. Ravi's. Initially, he has only shown the light to the whole world, this how these MEMS can reach to the pinnacle position in the future communication technologies. And this particular slide shows how this is superior than that of conventional things like your solid state or ferrite things. And he has reported also how this particular MEMS things, MEMS phase shifter things can have a very minimum losses, only 0.3 dB losses per bit in the X band, and in the W band minus 1 dB per bit, whereas you can have 3 to 3.5 times higher in case of FET. Or if you go to the ferrite things, you know ferrite has a very good characteristics, but it's bulky in nature. That is the only uh, disadvantage which will drive you the path for the future satellite communications or any airborne communication. Because satellite communication, you know that the payload things, the from the name itself you can understood that you are paying for the each and every kilogram of that. So if you can minimize the size of your circuit with the proper efficiency, then you obviously people will
I
choose
actually have a
your.
question.
Yes,
I
sir.
actually have a question. Hi, I am Devdeep. I have a question here.
Hello.
Actually, hello,
Yes, yes.
can you hear me now?
Hello.
Yeah.
Yeah, Dr.
So,
Sarkar,
Yes.
please go ahead.
yeah, sure. So sorry for the interruption. Actually,
Yes.
I looked at this slide
No
carefully.
problem.
Yeah, but the main issue over here is that what is the bit that you're talking about? So can you bit,
Okay.
like little bit explain more
Yes.
technically, because it's just going above our head.
Can I request both the speakers, like Ayan and Devdeep, to turn on our video so that
Yes.
the host can take a snap, because this is a
Okay.
part of our reporting. Okay,
Okay.
Arijit, can you please take a snap? You please turn on
Okay.
your video also at the same time. Yeah,
Yes,
Yeah,
yes,
and
yes.
then we will interact. Yes.
Yes, Dr.
Okay.
Sarkar, please go ahead.
Hello.
Yeah.
Should I? Huh.
Am I visible?
Hello, Devdeep. Can
Yeah.
you hear me? Suppose if you are taking
Yeah.
about the phase
Yeah.
shifter things, we are here talking about some phase shifter, which is say it's a switch line phase shifter. And if you taking about the switch line phase shifter, I'm talking about switch line phase shifter is mainly it's a digital phase shifter. Suppose if you want to design some phase shifter which will give you 11.25 degree, as an example, I am just giving 11.25 degree, then as a twice 22.5 and then 45 degree. So this is known as a single beat. And if you have to have some say n bit phase shifter, you have to integrate. And you know, as a RF
Okay.
person, that integration is not so easy. Just
Yeah.
for understanding, I'm just because you have to take care about that transition as well as that
Yeah.
what is the junction, because that T junction will play a very important role. You have to take care about all these things with the help of air bridge, or even your ground can also play a very important role if you enter into K band. So that's what people used to call it as a per beat. That is a notation usually.
Okay. So it's basically a notation, and it's in the context for the digital kind of basic.
Okay.
Okay. So I'll
Yeah.
thank you,
Should
and
I?
I'll
Okay.
let you.
Thank you.
Yeah. Please go
Yeah.
ahead.
Can I
Yeah.
go to next slide?
It's very.
Ah,
Yeah. Sure.
okay.
Very nice presentation.
Thank
I'm
you.
sorry.
Okay.
Yeah.
Thank you. Now, what are the technologies available at SCL if you want to have some phased array antenna? At a glance only, I just want to explain. One is silicon technology, another is gallium arsenide technology also. So for MEMS, you can have these two things parallelly. And for monolithic integration, suppose if you want to have this monolithic integrations with the help of this CMOS technology, you know that you need some PA, you need some low noise amplifiers, and various control circuits also, because you have to integrate the whole things. If you want to have some system on chip concept, or say antenna in package concept, AIP concept, you have to have some monolithic integration concepts also. Or if I just want to give some examples of, people are thinking about WSN or wireless sensor network, because in future you know that in IoT or 5G, WSN will play a very, very important role. And this particular slides I intentionally put just to show you how the phased array antenna is applicable in case of space. This messenger has shown this. Just see this X band phase shifter they have used, which has a that much of radiating elements is there. And this is the practical applications of this phased array antenna. And this particular mission was for 4 years, 11 to 15. These are the glimpse of some circuits which initially we have developed for to establish our silicon RF technology, for just to demonstrate how that whether my silicon, high resistive silicon, can be a viable substrate to compare with this standard microwave substrate like Rogers, FR4, all these things. So this is the X band balloon, and then dual band for GPS application 1.575 and 2.680, these two things. And this was for 8.2 gigahertz. Then as a system concept, as a depth of arrival, DOA concept is there. It's a very small receiver as concept has been at the front end antenna also we have connected. And this was also dual band. This particular initial slides also we have done intentionally this particular structures. Our main intention was first to prove whether silicon can be used for high frequency application. Then our second approach was that whether high resistive silicon can be used for multi-band operation. And then we have targeted for whether this particular silicon can be used for UWB application, that means for a broad band applications or not. And then as a vertical integration or a packaging techniques, whether I design my circuit in standard CMOS or say standard MOS, then sorry MEMS, then we need something which we need as a vertical integrations. And as a RF engineer, you know that this is known as a normal PTH. Or that PTH, that term here in silicon, people used to call it as a TSB, through silicon via. That is the same things, but that through silicon via, as you can understand, that this particular via now it will not act as a just a short circuit. It will act as a inductor. It will behave as some, it will provide some parasitic capacitance also. So you have to model it. So that's what also initially through and through efforts we progress with the standard 675 micron wafers, and then we fill it and then for high frequency applications, you know that high frequency applications, that wafer thickness should be minimized. And as a wafer thickness we taken around 300 micron that things. And our fabrication team has done a very, very excellent job, because if you want to have some thinning these things from 675 to 300 micron, this thinning is a very, very difficult, because you need a global thinning, and then this particular via hole you have to make, and after that that filling, and during this filling lot of problems will come in generally. Like sometimes you will find some unwanted voids will appear. Sometimes you will find your filling is not proper conformal in shape. So you can understand that how your device will spoil and your purpose will not be served. And not only that, suppose in case of everything is coming in a good fashion, now you have to calculate how much inductance I have to de-embed during my final device characterization. So that's what also I have to think about. Now look at this particular inductor, so which is not possible in case of CMOS things. Normally, if you look at this CMOS things, you know that in CMOS, my inductor has this much of basic elements are there, where the C sub, R sub, these are the unwanted things, but you cannot remove all these things completely. So if you look at this particular inductor, these two inductors, you just think this particular inductor is hanging. That means basically you are removing this part. And or in other words, you are basically enhancing the Q factor. And just like that, with the help of this hanging high Q inductor, you can have a very, very good performance LNA in case of high frequency applications. And one of the very primitive structures, if you look at any paper, book, anything, you will find that people will start with these things. Switch is a very, very common things. And so that's what you have to start. So as I have told already, that you have to go by this bottom to top approach. This bottom to top approach, you start with this inductor, then this particular switch, because these are the building blocks. If you are through, if you are succeeding with these blocks, then you have enough confidence. You will face a lot of problems. Process people have a lot of problems. Design, I will say, it is little bit easy in with respect of this process engineer. So you have to learn those process issues also. Nothing can be come out first time, because say hanging structure, lots of parameters will come, stictions will come, sagging will come, you will not understand initially. So apart from that things, you just think about how I will bias my circuit, how I will apply my actuation things. Usually in case of MEMS or RF MEMS, you will find that there are lots of actuation, but people prefers electrostatic actuation, which is very much compatible for IC business. And that electrostatic actuation needs some pad, needs some actuation pad, where you will apply your actuation or DC voltage, and with the help of that DC voltage, you know that pull-in phenomenon will happen. And at the one third of the initial gap, like look at this particular figure, this leftmost corner figure here, G0 is the initial figure at the rest position. This particular switch will act as a, you can say it's a two-state capacitor. This two-state capacitor, now this switch is in up state, and this particular up state switch, now it is offering as a minimum capacitor. When it will, with the help of this DC actuation, if I can make this beam snapping down, then this in between capacitance will enhance, and that downstate by upstate capacitor, that ratio is known as a figure of merit of the switch. So that will decide the performance of our switch, and with the help of those switch and phase shifter, you can think about how your channel is opening for the reconfigurable antenna. Now
Sir,
you
sir,
know
sorry to
that
interrupt. Can you just speed up a bit? You may have another 5 or 6 minutes to
yes,
present.
yes, it will be over.
Okay,
So
thank
you
you, sir.
just yes, just think about this reconfigurable antenna may be of various kinds. It may be reconfigured with the help of frequency, or in the with the help of polarization, in terms of polarization, or it may be of a radiation pattern, or it may be of some hybrid of anything. And with the reconfigurable antenna, this particular reconfigurable antenna can be realized with the help of either FET or HEMT or solid state, all these things are MEMS. And as I already told you, that how this particular thing, how the MEMS is becoming the superior rather than all this counter part. So it will show that how this reconfigurable antenna can be achieved with the help of MEMS. And here you can see there are very few works nowadays going on in our semiconductor laboratory, how the system on chip, this particular concept in various collaborative projects. either it's a biomedical, or in case of this is showing some on-chip antenna. These two are showing this is for chip-to-chip communication. Size was only 2 millimeter cross 2 millimeter. It was X band 9.45 gigahertz antenna, and this particular antenna, it was a UWB antenna. Its size is only 8 cross 11 mm, and this is a antenna which has been fabricated on liquid crystal polymer, which is flexible in nature. You can think about that how this is a capsule and how it is wrapped around this capsule, and how we have made the human phantom here with the help of different chemical things, and we have tested that particular things. So these are the real time example of this, how the MEMS things can be achievable. And now you can think the how that RF MEMS can be obvious for the future wireless communication. If you think about this future communication, you just look at this particular slides. This particular slide, this is taken from this particular paper. This paper from Yanansi also. This paper shows that how this, with the increase or upgradation of the various technologies, the quality of the connection or the quality of the connectivity is getting lower. So the evolvement of MIMO technology or the massive MIMO technology. I think one of the very eminent participant is there just now. He has interacted with me. He is expert in that particular field, Dr. Devdeep Sarkar, and he knows much better than me how this particular MIMO is will take over the whole world for the 5G communication, and that particular MIMO will require a lot of MEMS things also. So that is the things I just want to mention here. With the help of this particular table, you can see how the MEMS vector or MEMS differential capacitor has a lot of advantages rather than standard CMOS vectors. And you can enter in the field of terahertz also with the help of this technology. And you know that terahertz, this concept was first conceived by the Dr. Jesse Bose, Professor Jesse Bose. And here you can see with the help of the silicon micromachining, that means with the help of various waveguide structures, how you can make your conventional power divider, waveguides, your couplers, OMTs, all these things, even horn antenna, integrated horn antennas can on everything can happen with the help of this silicon micromachining, or in other words, this MEMS. So that is the things, and these are the references. With all these things, I just want to thank organizers and Arijit.
Thank you, sir, for such an elaborate and especially very well explained lecture. I'm sure all the participants will be immensely benefited from today's event. Now we'll have a
You can see this is the one paper snapshot I have put here. Dr. Jitendra Singh in 2015 has came here in our SCL, and he has seen all the activities, and then in the Times of India it has been published also. Okay, thank you.
Okay,
Yeah,
so
excellent talk. You have covered various aspects. I mean, even though your talk was on MEMS, but you have covered the peripheral things also. Very nice talk. I appreciate a lot on.
Thank you,
So
sir.
just one thing, you may comment because there are many UG students, there are few researchers. I'm happy to see there are few participants even from abroad. Okay,
Okay, sir.
so if you just comment on these MEMS as a switch with some of the other switches, for example, high frequency switches means we can use pin diodes, we can also use sometimes the optical switches. If you just compare your MEMS switches with this some of the other kind of switches in terms of speed, in terms of size, in terms of the pull-in voltage that is needed for MEMS switches. Yeah, just a overall lesson for the beginners, especially.
Sir, may I ask one question?
Yes.
Good evening, sir.
First, let him answer this one. Yeah. Hold on, please.
Can you kindly
Yeah.
wait? After this, he will answer your question.
Okay, sir, starting from that actuation point of view, actuation voltage point of view, it has one only demerit. It needs little bit more actuation voltage, around 20 to 30 voltage. And now people have started tackling these techniques by called as a pump circuit. So from externally, you will give only say 5 volt standard, and in the internal some ASIC is there, application specific integrated circuit is there, which will pump that 5 volt to 23 volts. So you actual operation of that MEMS circuit is happening in the range of 23 to 30 volt generally. But if you look at the size and all losses, then this particular MEMS things is superior than FET, PIN diodes and all these things.
Yeah, very good.
Oh,
Yeah.
okay, now that participant can go ahead with her question, please.
Yeah, someone was
good
asking
evening.
some question. Please go ahead.
Yes, yes. Good evening,
Can
sir.
you please
I'm Chandrima
introduce
Thakur.
yourself?
I'm Chandrima
Okay.
Thakur from Jadavpur
Yes.
University. I'm
Yes.
working on RF energy harvesting in wireless communication. So I
Yes.
just wish to know something regarding RF MEMS switch. You said that TR module is are replaced by RF MEMS switches in
Yes.
application part. You said. So I think these switches operate in similar way to conventional RF mechanical relays, right?
RF mechanical release, you are correct. Operating principle is same, but you know that
Can they be
normal.
used for high power applications?
No, I am telling you. Normal mechanical switch, it has some latching capability also, correct? And as well as it
Yes.
has some mechanical wear and tear problems also. But it has the another advantage is that it has a excellent high power handling capability, which doesn't have for RF MEMS. So everybody has their own merits and demerits. So like RF MEMS has demerits. One is it needs high actuation voltage. Second one is that it doesn't bear that kind of high power. And if you go to the third one, then its packaging and all these concern you have to take very tactfully. Normally it is packaged, you can say, in inline, or I will say WLP, wafer level packaging. Within the IC fabrication, that same line itself fabricated during the fabrication of the switch, at a time this packaging also it's going to happen. So initially it will be a little bit hurdle, but finally you know that the beauty of this MEMS process is that it's a batch processing. Once if you are through, then you will win the game, because at a time in a single wafer you are able to get thousands of devices, which is not possible in case of your PCB or your mechanical switch or anything. Am I clear, Chandrima?
Yes, I think the design process is a bit complicated, isn't it? Although these are easier to apply.
Design process, yes, it's complicated. Even people have reported high power RF MEMS switch is also there. Some little bit tricks are there. So that I have not covered in this particular presentation,
Okay.
but there are techniques by which you can
It's
enhance the power handling capability. And what we were talking about, that RF energy harvesting,
Yes.
there in RF energy harvesting, there is a huge scope of this RF MEMS, because you know that RF energy harvesting, your main antenna is working in the GSM band, 835 to 915 megahertz band. So in that
Yes.
particular frequency, you can design your antenna efficiently.
Okay.
Yeah,
Thank
can
you.
I
Thank you so
comment,
much.
Shangomitra? It's not complicated. It's not complicated. The design is, one-time process, but depending on the applications, you have to choose the different kind of pull-in voltage. For some applications, you need to think of the size and all. The most complicated part is to have, to get it fabricated in India. Okay.
Yes.
So on that aspect, Ayan is one of our resource persons. Okay. Yeah.
And is there any potential to develop it further for IoT? RF MEMS
Yes,
can
yes. MEMS can be
please
used.
be
It's
applied
a
for IoT?
very good application for IoT, because in IoT smart city concept is there, and in IoT WSN wireless sensor modules is there. And if you want to have some wireless sensor modules, you have to have a batch to batch antenna, and very good connectivity between your sensor and antenna will be there. So there MEMS will play a very important role. IoT as well as in 5G also, even in terahertz. That's why the title of that presentation was the possibility of MEMS in future this communication.
Okay. Thank you so much.
Okay, thank you. Any more questions from any participants? There are some few questions in the chat box. One is like the highest operating frequency achievable with RF MEMS. I think sir has already answered that. We are going beyond terahertz and above. And sir, I would like to ask one question, sir. In this terms of RF MEMS, how much?
In lithography techniques.
I think we already answered that.
Okay, highest operating frequency with the RF MEMS is still nowadays. Hello?
Yes, sir.
Up to 110 gigahertz. Still, people have reported. Up to 110.
Hello.
Yes, sir. You are audible. You go ahead.
Hello.
Hello.
Hello,
Yeah,
sir.
Ayan, I am Deven Kumar Sharma from SEC Ahmedabad. Yeah, have you
sir,
thought of any? Yeah, I'm fine. Have you thought of direct space application of this RF MEMS?
That is the system application. One is that terahertz, that things, and another is that suppose if we can build some phased array antenna, then we can have some.
But in phased array, you have to go for 3-bit or 4-bit phase shifter,
Yes.
because generally in our
Yes,
application,
yes.
it's a large,
5-bit
generally 5 or 6. Yeah. So 5-bit can we make here?
Yes, sir. 5-bit. We are now design is there. We have
Same issue
loaded.
probably.
Yes. So we are targeting 30 gigahertz 5-bit switch
Yeah.
line.
Okay. Thank you.
Thank you, sir.
Okay, I think some questions are there, but we can take it up later. You can, sir will share his email ID. You can always get in touch with sir. Thank you all of you.
Yes, yes.
Now we'll just conclude.
Yes, frequency of operation you can tell 110.
Yeah, that is 110. Then
what the second question is that lithography, that is completely a fabrication. It's a big topic. You need a separate lecture for that.
yeah, definitely we'll try to
Yeah.
get you once again, sir, on this topic.
Yeah.
No, that is
Yeah, but note down his email ID and just email him regarding the queries, because I see many other unanswered things,
Yeah,
but
that-
nothing will be unanswered. Everything will be answered.
Okay.
Yeah,
I will try
offline.
my level
Yes.
best. Yes.
Okay, so I'd like to call Professor Anu Muhammad to just give a vote of thanks and conclude the session.
Good evening to one and all. Am I audible?
Yeah, audible.
Yes,
Go ahead, sir.
Thank you, sir.
Thank you, sir. Thank you. So, good evening to one and all. On behalf of MTT-S Micro Theory Techniques Kerala section, I would like to thank today our guest of honor, Mr. Ayan Karmakar, SCL Chandigarh ISRO, for this enlightened session. Really, we are thankful to you, sir, for sharing your experiences, both theoretical and practical, you had while design of various subsystems at SCL Chandigarh, and
Thank you,
also
sir.
the current state of art in RF MEMS, where the technology lies right now. Yes, definitely. I feel that the students who attended your session, you have tried to show some justification and interest to them and definitely they will consider these for implementing any RF circuit design. And you also have shown justification why MEMS is an inevitable part of RF millimeter wave application. The student in attending our webinar and session to that level. And I request especially the student members make use of these kind of webinars, which will be again coming in the future, and may thereby make your basic fundamentals strong. With these words, I am cut shorting, and I would like to transfer this virtual podium to Saha sir and Mr. Ayan Karmakar for further proceedings.
Okay, thank you.
I would like to.
I just want to share a few things before concluding. All of you who have attended this session will be sending feedback forms. Please give your feedback, and also we'll be arranging participation certificates for all participants. And once again, thank all of you. Hope you enjoyed the session, and we'll also look forward for all of you to join in our future sessions as well. Thank you. Shah sir, if you want to say something, you can continue.
Nothing to say more. Thank you very much for attending, and there will be few more of this kind this year as well as probably next year, because this many restrictions will be there in different fronts in terms of our traveling and all. So attending conferences, seminars, symposiums, the way we used to do won't be happening. So we'll take this initiative forward, and we'll keep you posted regarding further events that we'll be going to host future. Stay tuned with MTT-S Kerala chapter, and as we do in a real event, we always give a felicitation to the speaker at the end with a memento, which is not possible at the virtual platform, but we'll be handing over a memento to Ayan later on through courier. So you may just think that I am giving a memento to Sri Ayan and he is receiving it. You can think of this virtually, and we can have a group photo. All of you can turn on your video for the time being, so that we can have a group photo, virtual photo, of course, for our reporting. Thank you very much. Yeah.
Thank you, sir.
Arijit, can you please?
Yeah, please. Thank you, everyone.
Yeah.
Okay, thank you, everyone, for attending.
Thank you.
Yeah.
All people, stay safe, take care of yourself and your family, and a very good night to all. Thank you.
Yes. Thank you.
Good night.
Bye bye.
Everybody. Yes. Bye, sir.